One more thing about independence. There is an exception that we can use to make our calculations easier. When selecting small samples from large populations, we can treat dependent events, those that are without replacement, as independent events, those with replacement. Obviously, the independent event calculation just involved the probability of A times the probability of B. We didn't have to be concerned with conditional probability. Dependent events involve conditional probability. It's a little more complicated calculation. So the rule states, if the sample size is no more than 5% of the population size, we can treat the events as independent. So in other words, using our notation, if the sample size n is no bigger, so less than or equal to 5% or 0.05 times our population size, which is capital N, if this holds true, then we can use the easier calculation and not be concerned with conditional probability. So let's look at an example to help understand this. So we have a 12-person jury to be selected out of 20,000 potential jurists. Registered voters is usually where they get those lists. Of 4,000 of the potential jurists are Hispanic, so we know that 4,000 are Hispanic. What is the probability that all 12 of the chosen jurists are Hispanic? So obviously, when we first read this, we would realize that these selections are dependent. Once you've selected the first person, you're not going to put that person's name back on the list before you select the second person. It's without replacement. Without replacement. That makes sense. When you're choosing people to serve on any kind of committee or something, you definitely don't want to end up selecting the same person twice. So you would set that name aside, and we know that makes those dependent events and without replacement. So in that case, normally we would say, well, this would be the probability of, and I'll just use an H, Hispanic, for the first jurist, and a Hispanic chosen for the second, and ... Instead of writing them all, I'll just do this, and a Hispanic chosen for the 12th jurist, okay, which we know we would write a very complicated probability here. I'll just sort of start that, but it would be the probability, the first one, times the probability of the second one, given that the first one was already selected, times the probability of the third person selected being Hispanic, given that the first one and the second one were Hispanic, ... You can see how that can get more and more complicated. Writing this out numerically then, the probability of selecting the first person for the jury and they're Hispanic, well, there are 4,000 Hispanic names on our potential juror list, and we have 20,000 names on our list total. So that would be probability that the first person selected was a Hispanic. Alright, then our next one, we would put that person's name aside, so there would only be 3,999 Hispanic people left on the list, and there would only be 19,999 people left on the list. So that's the conditional probability here. The probability that the second one selected is Hispanic, given that we already selected the first one that was Hispanic. Okay, and so you can see how this would go. 3,998 over 19,998. And now I'm not going to write those all out, so I'll just put an ellipsis here to indicate that's where that's going. But let me show you why, a little bit about this so you can start understanding why we can use the rule. If you calculate this to a decimal, this is 0.2. The next one is 0.1995998 and would go on, but that's just what displayed on my calculator. The next one, 0.199199992. So you can see that I think I missed a 9 right in here. There were 3 9s. There we go. That these are so very close to 0.2 that ultimately, once this calculation's done and you round, this is going to be insignificant. And the reason is because of the rule. So let's look at that calculation. We said that if n is less than or equal to 5% or 0.05 times n, then we can treat these as independent events. So let's see. N was 12. Our sample, we're selecting, there are 12 jurists. Is that less than or equal to 0.05 times 20,000? Okay, well, is 12 less than or equal to 0.05 times 20,000? That's 1,000. So yes, this is true, and so we may use the rule. And now why would we want to do that? Well, let's look at that calculation again. Now we will say the probability that the first person chosen for the jury is Hispanic, and the second person chosen is Hispanic, and then we said ... and the 12th person chosen is Hispanic, will just be equal to the probability that the first one is Hispanic times the probability that the second one is Hispanic, because we're going to treat these as times, I'm going to continue down here, the third is Hispanic, we get to treat these as independent events. No conditional probabilities. Okay? So the probability that the first person chosen is Hispanic was 4,000 Hispanic in the group out of 20,000 people. And if we're not worried about conditional probability, then that's true for the next one. Remember, we're treating it as though we are replacing. So there's no condition. And all the way down, we'll have 12 of these, right? So in fact, if we have a sequence of 12 of these, a product of 12 of these all multiplied, there's a much easier way to write this. To the 12th power. And recall, we found that value a little bit earlier. It was 0.2. So 0.2 to the 12th is our result, and that would be 0.000000004, I believe. I think there are 8 zeros here. A very, very, very small probability that all 12 selected would be Hispanic. So when we have small sample sizes relative to, that's what the rule says, relative to our population, the sample size is just 5% or less of our population, then it's unnecessary to worry about the conditional probabilities, and it certainly makes our work a lot easier. And we will be doing this. Now, the problem won't state that you may consider these events as independent. Generally, it's left to you to understand, or to run through this little calculation here first to determine whether or not you can do this. So that's something that you'll get in the habit of checking.